It is the most successful construction system in human history. A simple plastic brick, so ubiquitous we often take it for granted. But look closer, and you'll find an engineering marvel that rivals the aerospace industry. We are talking about the Lego brick. To the naked eye, it's just colorful plastic, but to an engineer, it's a masterclass in clutch power. This is the specific force required to hold two bricks together while still allowing a child to pull them apart. For 60 years, every single brick produced has been designed to fit perfectly with any other, whether it was made in 1958 or this morning. This level of cross-generational compatibility requires a degree of precision that is frankly absurd. We are measuring tolerances down to 2 micrometers, that is 0.002 millimeters. For perspective, a human hair is about 50 times thicker than the margin of error allowed in a Lego factory. If the mold is off by even the width of a dust model, the bricks won't click, they won't stay, and the system collapses. Today, we go inside the highly guarded world of plastic injection molding to see how sand and oil are transformed into the world's most precise geometric tools. This is the anatomy of the perfect fit. The journey begins not with a brick, but with a grain, specifically granules of acrylonitrile butadiene styrene, or ABS. This isn't your average plastic. A-BS is a pteropolymer chosen for its unique trifecta of properties: the strength of acrylonitrile, the impact resistance of butadiene rubber, and the rigid, glossy finish of styrene. In the Lego factory, these pellets arrive by the ton, sucked through massive overhead pipes at speeds of nearly 60 miles per hour. But before they reach the machines, they must be perfectly dry. Even a trace amount of moisture inside the plastic can turn into steam during the melting process, creating microscopic bubbles that would ruin the structural integrity of the brick. The pellets are dyed using high-concentration pigments, only 2 grams of ink for every kilogram of plastic. The colors must be identical every single time. A Lego red from 10 years ago must match the red on the assembly line today with 0 deviation. This chemical consistency is the foundation. Without the right molecular bond, the plastic would shrink or warp as it cools, destroying that 2 micrometer precision before the brick is even born. The real magic happens inside the molding machines. Massive hydraulic titans that exert pressures of up to 150 tons. Inside these machines sit the most expensive components in the factory, the molds. Each mold is a block of high-grade hardened steel machined with such extreme accuracy that they cost hundreds of thousands of dollars to produce. The ABS pellets are heated to 450 degrees Fahrenheit, roughly 232 degrees Celsius, until they reach the consistency of thick toothpaste. Then, under immense pressure, the molten plastic is injected into the mold. It takes only a few seconds. To prevent the plastic from sticking or warping, the mold is instantly cooled by an internal network of water pipes. This is a violent process, metal screaming against metal, extreme heat meeting rapid cooling, yet the result must be a perfect, smooth surface without a single burr or sharp edge. Every stud on top and every tube on the bottom is formed in this split second. The pressure is so high that if there were even a microscopic gap between the two halves of the steel mold, the plastic would leak out, creating flash. But in a Lego factory, flash is non-existent. The seal is absolute. Why do Lego bricks stay together? It's a principle called interference fit. If you measure a Lego stud, it is slightly, just slightly, larger than the space between the tubes on the underside of another brick. When you press them together, the plastic slightly deforms. That tiny bit of elasticity creates friction, which we call clutch power. This is where the 0.002 millimeter tolerance becomes critical. If the stud is too large by 5 micrometers, the brick will be too hard to pull apart, potentially snapping the plastic. If it's too small by 5 micrometers, it won't hold the weight of a build and the model will crumble. This is why Lego molds are kept in ultra-secure climate-controlled vaults. Temperature fluctuations can cause the steel to expand or contract. Even the friction of the molding process slowly wears down the metal. When a mold reaches its limit, usually after several million cycles, it is retired and encased in concrete to ensure its designs never fall into the hands of competitors. This is the gold standard of toy manufacturing, a level of mechanical engineering usually reserved for high-performance engines. In a factory that produces over 2 million bricks every hour, human hands rarely touch the product. After the molding is complete, the bricks are dropped onto conveyor belts and whisked away to the sorting area. Automated robots, guided by laser sensors and high-speed cameras, monitor the flow. If a single brick deviates from the programmed weight or shape by a fraction of a gram, it is instantly blown off the line by a precise jet of air. These rejected bricks aren't thrown away. They are ground down, melted, and recycled back into the start of the process, though never for elements that require the highest precision. The logistics are staggering. Thousands of different shapes, from the classic brick to tiny Technic gears and minifigure heads, are sorted into massive silos. The factory floor is a choreographed dance of autonomous vehicles, small, driverless carts that navigate the warehouse using sensors to pick up containers of finished parts and deliver them to the packaging lines. It is a closed-loop system designed for one thing: the elimination of human error. In this environment, the machine is king, ensuring that every piece is a carbon copy of the last. Not every brick is just a solid block of color. Many require intricate designs, the expressive faces of minifigures, the controls on a cockpit, or the logos on a race car. For this, LEGO uses an advanced version of pad printing. A silicone pad picks up ink from an etched metal plate and stamps it onto the plastic. But this isn't like the printer on your desk. Because the surfaces of LEGO parts are often curved or multi-angled, the machines must account for distortion in real time. The ink itself is a specialized formula that bonds chemically with the ABS plastic, ensuring that after years of play, the design won't peel or fade. For more complex parts, like dual-molded legs where two colors of plastic are fused together, the process is even more intense. Two different colors of molten plastic are injected into the same mold in a two-stage process. This creates a permanent bond between the colors with a seam so fine it's impossible to feel with a fingernail. It's a level of detail that turns a simple toy into a piece of industrial art. Every eyeline, every belt buckle, and every button is placed with sub-millimeter accuracy. Before a set ever reaches a store shelf, it must survive the torture test. LEGO's quality control labs are places of systematic destruction. Bricks are subjected to extreme heat, mimicking a hot car in Phoenix, and extreme cold, mimicking a basement in Norway. They are crushed, pulled, and bitten by mechanical jaws to simulate the roughest play imaginable. One of the most famous tests is the clutch test, where a machine repeats the process of snapping and unsnapping two bricks thousands of times to ensure the friction remains constant. They also test for chemical safety. Since children often put these bricks in their mouths, the plastic must be non-toxic and resistant to saliva. Only about 18 out of every 1 million bricks fail these rigorous standards. That's a failure rate of 0.0018%. If a batch doesn't meet the target, the entire container is scrapped. This obsession with quality is why you can still use LEGO bricks from the 1960s today. They don't just build toys, they build legacies designed to outlast the people who buy them. It is the ultimate testament to engineering durability. From a handful of oil-based pellets to a high-precision interlocking system, the journey of a LEGO brick is a triumph of modern manufacturing. What began as a wooden toy company in a small Danish workshop has evolved into a global standard for precision. Consider this math. 6 of the standard 2x4 bricks can be combined in 915 million different ways. That level of mathematical infinity is only possible because of that 0.002 millimeter tolerance. Every time you hear that satisfying click, you are experiencing the result of millions of dollars in research, ton-level hydraulic pressures, and the world's most precise steel molds. It is a bridge between the digital world of design and the physical world of play. The LEGO brick isn't just a toy, it's a universal language of engineering. It proves that with enough precision, enough care, and enough science, you can build anything. From a simple house to a life-size Bugatti Chiron that actually drives, it all starts with the absurd math of the perfect fit. This is how it's built. This is the art of the brick. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.